believe, on Wednesday last week, was looking at the oxidation of carbon side chains, or your benzylic positions. Those benzylic positions have some particularly interesting chemistry. We had on the previous slide. As long as we have any benzylic hydrogens, turns out that an oxidizing agent is strong enough to go through and completely oxidize that position. So in the case of toluene, if we react it with our oxidizing agent, we can convert that across to just straight benzoic acid. Okay? So it's able to cleave off all those extra hydrogens. If we up the kind of steric hindrance-ness, if you will, up to that alkyl benzene, we still have a benzylic hydrogen. As long as we have that benzylic hydrogen, we can go through and oxidize that position. And because of that benzylic nature and the reactivity of our oxidizing agent, we will completely oxidize that down to, again, benzoic acid. Okay. One of the things that has always kind of perplexed me, but never quite enough to actually look up, was what happened to the rest of the carbon pieces. I still haven't looked that up yet. Okay. You're not responsible for it. You're not responsible for the mechanism. You don't need to worry about it. All you need to know is that if you have a benzylic hydrogen and you put an oxidizing agent near it, it's going to oxidize the crap out of it. Take it all the way down to the benzoic acid. Don't worry about the other pieces. When it comes to the next sequence, in fact, I would say the middle two, your alkynyl benzene and your alkynyl benzene. Both of those, you should know, go to a benzoic acid using permanganate, because that is doing the oxidation of that alkene, okay, or that alkyne pi bond. So you've seen that one before. The last one I would say is actually a new addition, because typically when we added an oxidizing agent to a ketone, what happened? Nothing. Nothing happened. Okay. But again, due to that benzylic position being reactive enough, as long as we've got that oxidizing agent present, it'll go all the way down to the acid. Okay. So all of these will result in the benzoic acid formation. Just like oxidation, we can go through and do reduction. It is very hard to go through and make the nitrogen or put on an NH2 onto an aromatic ring. Okay? In fact, we cannot do it directly. We have to go through a reduction process first. The main reason being is that nitrogen would act as what? A base or a nucleophile. And everything that we've talked about so far, our aromatic ring acts as a nucleophile. So putting two nucleophiles together isn't going to do anything. Okay, so we can't just directly do an EAS reaction for the nitrogen. So what we'll do instead, which is kind of hidden on the slide, which is nice, is that we will convert it to a nitrobenzene structure. Okay, so how can I get a nitrobenzene? So there's our benzene and there's our nitro. What's that? We do need a lot of positive nitrogen. Sorry, I started to definitely heard something different. We do need a positive nitrogen as our nucleophile. But where do our electrophile, where do we get it from? Right. Really what we need is the nitronium ion. The nitronium ion comes from nitric acid reacting with sulfuric acid most typically. Okay. So nitric acid in the presence of sulfuric acid will give us our active electrophile, the nitronium ion, which we can then react with our ring to go through and give us our nitrobenzene structure. Once we have the nitrobenzene, we can reduce those oxygen bonds. Okay, so this is something that is always kind of misleading, is that we almost always write the nitro as just NO2. Very rarely do you actually see it written out in full gory detail, which is actually this. Okay. Why is that particularly relevant here? Well, what do we have between the nitrogen and the oxygen? Resonance and a pi bond. What can we do with the pi bond? We can reduce it. And that can be done with a variety of reducing agents, the two big ones, hydrogen and palladium, typically not used. Why would we avoid using hydrogen and palladium?
Because it's more expensive.
Actually, yeah, it probably is more expensive here. Where else have you seen hydrogen and palladium used? Reduces alkenes, carbonyls, it reduces a lot of things. It's not a selective reducing agent. So using hydrogen and palladium is not the best option for going through and reducing. So more commonly you end up seeing that bottom choice are HCl and iron. I will caution you that there are a lot of metals that can be swapped in there. So iron is a very common one. The other common one I've seen in there is tin. Okay. Similar to, I kept screwing it up last week, Clemenson reduction. Okay. It's like a dissolving metal reduction. Either way, we get down to the amine structure shown. What's the common name for that compound? Not up there, is it? Good. Relevant for today's lab. Aniline. Okay. Aniline has some particularly synthetic or interesting synthetic uses, which hopefully shows up on the next page. Yes, it does. If we take a look at aniline, it's got all sorts of crazy things that can potentially go sideways with it. One of the more interesting things is something referred to as the Sandmeyer reaction, which is a reaction that happens after we convert the aniline over to a Benzenediazonium ion. So we'll take our aniline structure and we'll react it with the sodium nitrite in the presence of acid. This will convert it across to our diazonium ion. Once we have the diazonium ion, we can then add in pretty much any source of nucleophile, and we can do a substitution for whatever that nucleophile is. In this case, bromine. The Sandmeyer reaction exclusively references the copper catalyzed version of this. Okay, so we do need that copper species present to go through and do this reaction. The diazonium, just to give you an idea of a target here. We've seen these before. Why might the diazonium be a particularly useful species and particularly active against nucleophilic attack? Yeah, we've got a really good leaving group with the nitrogen gas. Okay. Why is this reaction further a little bit interesting? Okay. 2 hours actually isn't that long. When it comes to reactions, it's actually not too bad. How many times have we seen a substitution reaction on a benzene ring? Particularly a direct substitution, a nucleophilic substitution like this. It doesn't happen. Okay. So it's kind of a neat reaction. Probably one of the reasons why we ended up naming it after that discoverer, or Sandmeyer. Okay. So how do we get to the diazo compound? We said that is the result of our very first step. Okay. This is a pretty thoroughly exciting mechanism to go through and do, and I only kind of want to do it, particularly because I know in the subsequent slides it's already fully up there. Okay, so let's approach it slowly, hopefully without cheating for those of you that printed it out. Okay. So if we take a look at our first sequence of reagents, we're looking at aniline and the presence of NO2 minus and the presence of HBr. What's the first thing that we notice for reactivity, or that you notice for reactivity? Is that a nothing? we have a negatively charged oxygen. Okay. And as Cassie was pointing out, we also have a strong acid, which is reactive because it supplies not just a hydrogen, a proton. We get more, so we have positively charged hydrogen. So our very first step will be react those two species. And this is where things get a little bit odd. Okay. Now what? There's a perhaps blatant hint. So there's an interesting idea. We still have a strong acid floating around. We should try and protonate. So one option is going through and protonating the nitrogen.
I mean, from
The other one. That's a longer arrow. Give me a second here. So that is one option. So let's take a look at some of these products. I wouldn't panic about drawing these out necessarily yet. For those of you getting excited about that. Okay. And let's not forget our target. We're trying to aim for the diazonium, which looks like this, right? Our diazonium product has how many nitrogens in it? 2. How many nitrogens do we have in our reactants? 2. So those nitrogens need to connect to each other. Okay. The blue nitrogen in our diazonium is most likely what nitrogen in our reactants? It's probably the nitrogen coming from our aniline. Okay. What is that nitrogen going to have to act as? It's probably going to have act as a nucleophile. So Matt, your suggestion of the acid protonating the nitrogen isn't necessarily a wrong one, and it actually will frequently happen. But what does that end up doing to our nitrogen from our aniline? It gets rid of the nucleophilic characteristics. Okay? So it's not that that's wrong per se, but that doesn't take us anywhere productive. There's something else that we should evaluate on potentially why that isn't as reactive as we might guess. What can we do with that nitrogen? There's resonance stabilization with those lone pairs, making them less basic than we might anticipate. Okay? So while that was an interesting thought, it didn't work out so well.
It's less basic. Is it possible that it would act more as an acid and get picked up by negative oxygen?
It is less basic. That does not mean that that nitrogen will now all of a sudden become acidic. No. We still have that acid floating around, though. We had a decent idea of having a nitrogen or a negatively charged species picking up the hydrogen. We did one negative, we did one nitrogen from the ring, and we said that wasn't the greatest option because we know we need it to be nucleophilic. So we could potentially draw from one of the oxygens. Okay, there is also another nitrogen in that other structure. So let's see what happens. How do I want to color code this? We'll do 1, 2, and 3. So far, so good? I might easily make a mistake. I've never tried to do this before. Yeah? Which of those is the best product? Why the blue one? We have a really good opportunity as a leaving group coming off of that blue one, which could then lead us to nitrogen with a lone pair, double bond to our oxygen, double bond, or lone pairs. Positively charged nitrogen, which could work really well with our electrophilic nitrogen, our nucleophilic nitrogen from our aniline. Why is this also further a reasonable option? Resonance in a similar fashion to the, there it is, thank you, the acylium ion. Okay, so we've got a similar stabilization coming out of that position. What happens with the purple one? Is there any resonance to stabilize that positive charge? No. Do we have any leaving groups? No. So that purple one is really pretty horrible because we've got no resonance and no leaving group. How about the green one? Is resonance, but that doesn't really do us any good. If we look at our overall pieces, we'd end up with our nitrogen missing its octet, okay, and no leaving group, no way to stabilize that further. Okay. It's this kind of processing that you should be thinking about and working through when you look at a problem. What hopefully you'll be able to do through enough practice is that when you look at these reactions, you are thinking about all these options, you've drawn them out in your head, and you can see where they're going to go. So ideally, you would have done in your head the purple one and said, that was a horrible option, and not have drawn in anything. The blue one, you might have gone through and said, well, I had a leaving group, maybe I need to start drawing that piece out and see where it could potentially lead. The green one, you might need to draw that one all the way out and again see that we really don't have any good options. The end result is that we now have that blue structure as our possible reaction. Okay, I still have a reactive species with a positive charge. Which atom is the electrophile? Nitrogen or the oxygen? Why the nitrogen? The oxygen has a positive charge. The oxygen being more electronegative than the nitrogen is very likely going to take that electron density away. And so what we end up looking at is our first worst, is that what we called it, first worst? Resonance structure to give us some information about our reactivity. Why is that one worse than the one on the right? There's positive charge in both those structures. Why is the Lewis structure on the right the best Lewis structure? You need to know these rules. Octets. Okay. The nitrogen in the red box has its octet satisfied. So does the oxygen. The nitrogen in the blue box does not have its octet satisfied. That structure is technically a bad resonance structure. Okay. We now have an electrophilic nitrogen. So what should we go through and find? How about something nucleophilic? Go through and attack, and what we would end up with, we would hope would be our final product. And of course it's not, for those of you getting too excited about that. Okay. So far so good? Okay. Is this our diazonium product? No. What needs to happen to get to the diazonium product? need to lose 2 hydrogens and the oxygen. That ringing any alarm bells? Like, that looks an awful lot like water. Okay. We do have some acidic hydrogens on that nitrogen, but they aren't particularly acidic, so they probably wouldn't very likely protonate the oxygen. So without a strong acid, we're kind of stuck here. Do we have a strong acid? Yep, we're in the presence of the HBr. So we'll end up going through a sequence of protonations and deprotonations. Okay, so if you liked all of those enol chemistries, actually it would probably be this way. One pair, hydrogen, double bond. This can push in, push that out, right? Through another sequence of protonations and deprotonations. Now what can happen? And we can get our diazonium product with the kick out of water. Lovely mechanism. You'll notice that I shorthanded a lot of that. Any ideas why? It's really, really long. Okay? So if you want to see the details of those, that's what the next few slides are. Your textbook has them as well. We go through in the first sequence to form your nitronium ion, or sorry, not nitronium, the nitros, whatever that word says, nitrosonium ion. Remember, the nitronium ion is NO2. Okay, this is only NO. That can react with our amine. We then have our nitrosamine, which can then go through a sequence of protonation steps in the last sequence around to end up with our diazonium species. The diazonium, again, particularly useful because if we break that carbon-nitrogen bond, we end up forming an incredibly stable nitrogen gas molecule, and we'd have a reactive electrophilic carbon. Okay? It can't happen on its own. Something must initiate and force it to happen. That's where our copper catalyst and our strong nucleophile come into play to help out. Okay. What nucleophiles work? Well, we got a whole smattering of them. Okay. Some of the more interesting ones, I think, in my opinion, would be the last two. Why would the last two be interesting? Doesn't really have anything to do with leaving group ability. How did we get the diazonium compound? Where did that come from? Our amine, which came from our nitro, which came from it's an awful lot of steps. What did we start with? Benzene. What did we end with? Benzene. You might say, well, that's dumb. Why would I do all that work? Okay. What have we done at that position? It is now permanently blocked by some piece. So if I wanted to do chemistry somewhere else on the ring relative to something else, I have a way to block and prevent something from reacting at that site. Okay. That is a lot of chemistry to have to go through to do that, but we could theoretically do it. Okay. That's why I think that one's kind of a neat one. questions on that aspect? Since there's some weird looking faces at me. Okay. Why is the next one kind of neat? As a hint, it's kind of neat for the same reason as our nitro reduction is kind of neat. Why was the nitro reduction kind of neat? We ended up putting a nitrogen attached to our ring, and nitrogens typically act as nucleophiles. Well, a ring is a nucleophile. There's no easy way to put a nitrogen on. Why is that last one interesting? Our phenol. Oxygen's usually a nucleophile. Okay. So I've gotten a nucleophilic atom attached to a nucleophilic atom. Okay. Kind of a nice little deal. Fluorine, not typically a good option. Why? Chemistry available for our fluorine compounds is pretty limited. Okay. Unless you're looking at, say, like Teflon. Okay, so not a particularly useful compound. The next one that I would say is kind of a nice one would be that middle one. Why is that one neat? Again, with the subtle hints. We now have a carbon, which isn't typically a nucleophile in general, but I've now extended the carbon structure. I can then potentially get that carbon to be reactive and extend my structure to larger and larger things. Why would I ignore, for the most part, A, B, and D? What do you mean pretty much the same?
They're all good leaving groups.
All good leaving groups. We're off of a ring, so they aren't going to act as very good leaving groups off of a ring.
Isn't it just like halogenation?
Getting at the right idea. A, B, and C, or A, B, and D, to get those, I had to go through with a benzene ring, nitrate it, reduce it, do some crazy weird Sandmeyer diazo stuff, and then I could put those three potential groups on. Or you can do a regular halogenation from step 1, EAS mechanism. To get a bromine on, what do I need? Br2 and FeBr3. Done. One step. Why bother to go all through all that trouble? Okay. That why bother might have to do with locations on the ring, which is kind of what chapter 23 is looking at. Okay. But in general, those options aren't going to be super common because we don't need them as frequently. Okay. There are easier ways to put those halogens on. Kind of makes sense? Okay. So there's our big EAS summary. Be cautious of some sneaky chemistry, and we will talk about these as they pop up. You got to watch out for that acid-base chemistry potentially sneaking in there and messing with your reactions. Be on the lookout of substituent conversions. For instance, I can do an alkylation by doing an acylation and reducing it. I can get the aniline by putting on a nitro and reducing it. So look for those kind of secondary chemistries to go through and convert a substituent across to something else. Last one, your Sandmeyer is also a substituent conversion. We can convert your nitro across into a variety of other pieces. Kind of, sort of? Okay. Just as a general horrible question to ask, how many people have read chapter 22? Not too bad. Just curious. I know it says quiz. We're just going to do it as kind of a breakout, figure things out. I want to see the answer to this quiz up on the boards. Okay. There are 8 possible answers that I want to see on the boards. Okay. There's a lot of people here. Yep, there are 8 possible answers. Okay. We're not looking for the product. Decide on a product. So you should be aware of what each of these reagents does. Go through and just do it. Do the substitution. Don't worry about it being the exact product. Do the substitution somewhere on the ring. See what you get. Go through and draw intermediates. as if you'd done the mechanism all the way. And then what we'll do once we've got steps 1 and 2 done, we'll then go through and look at each of them and try and answer question 3. Is there a better answer than others? You want a little jump start?